This is AI with Justin. So far in this series, we've covered hot field networks, Boltzmann machines, deep belief networks, and autoencoders. In this video, I'll be covering GANs. I'll explain some theory connecting GANs to the previous models, overview GAN architecture and training, mention training challenges, summarize a few variations which can mitigate these challenges, and lastly, discuss how GAN performance can be evaluated. Before we get into details of how a GAN works, I want to make some comparisons with the previously covered models. I'll do so in the form of categorization. First, let's make the distinguishment between probabilistic and non-probabilistic models. A probabilistic representation includes uncertainty in probability estimation. This means that probabilistic models are stochastic, whereas non-probabilistic models are deterministic. Each of the models we've covered so far, except for hot field networks, are probabilistic models. Another distinction we can make is the difference between explicit and implicit probabilistic models. Each of these remaining models could be classified as an explicit probabilistic model, meaning they provide an explicit parametric specification of the data distribution they are trained upon. Or in other words, they directly optimize the likelihood function of the data they produce given their observations. For example, reconstruction error is a direct observation taken from the data itself, and this feedback is commonly used to adjust the network's weights to fit the maximum likelihood function. GANs do not entirely fit within this categorization. Rather, they can be classified as implicit probabilistic models. Models of this class do not specify the distribution of the data itself, but rather define some stochastic process that attempts to simulate the data without any direct reference to any likelihood gradient. This is important because by avoiding the need to develop a lower dimensional intermediary representation of the training data, GANs are able to model the distribution of the training data directly from the data itself, rather than an estimation of data likelihood. It is this characteristic which allows GANs to generate higher resolution output than VAEs. I'll return to this later, but for now, let's take a look at the architecture and training process of a GAN. There are numerous variations of GANs, but what comes to mind for most people is a DC GAN, or Deep Convolutional Image Generating GAN. Let's use this as our example. GANs are composed of two main components, a generator network and a discriminator network. The discriminator is a standard CNN classifier which classifies input as either belonging to a distribution or not. For example, the discriminator for hot dog GAN, which generates hot dogs, would classify if an image included a hot dog or did not include a hot dog. The generator is an inverted CNN, which receives noise as input and outputs an image, or in the case of hot dog GAN, an image of a hot dog. During training, the discriminator and the generator are trained simultaneously in an adversarial minimax game. The discriminator is trained on inputs from the actual data distribution as well as fake data from the generator. It seeks a low error rate. The generator is trained on the feedback provided by the discriminator, seeking a high error rate. In the case that the discriminator is a binary classifier, the ideal performance target for the GAN is a 50% error rate. This means that the discriminator's guesses are random and that the game has reached a point called the Nash equilibrium, where no player in the game can improve their results from a change in their actions. Returning to the comparison of GANs and VAEs as implicit versus explicit probabilistic models, notice how a VAE's decoder, which is analogous to a GAN's generator, maps input from a latent space compression to the final output, whereas a GAN maps input directly from the noise input to the final output. An autoencoder's transformation of raw data through the encoder to the decoder is typically not a lossless process. As a result, even a perfect decoder could not perfectly reconstruct the input. This is the fundamental difference that I was referring to earlier, which allows GANs, as implicit probabilistic models to produce higher resolution images. The GAN training process that allows it to achieve such detailed results doesn't come without challenges. One of these challenges is that, in practice, GAN training can be very unstable. Whereas VAE training is supported by the lower bound of the log likelihood of the data, GAN training is not. Rather, the generator's interaction with the discriminator is an estimation of the lower bound of the log likelihood of the data. In this sense, we can make comparison between GAN training and the wake-sleep algorithm from episode 4. Anytime we are estimating a gradient, rather than directly measuring it, training is likely to face issues with stability. Further, given that this estimation is typically communicated in the low bandwidth form of a binary decision, it can be difficult to maintain an accurate estimation throughout the training process. In an attempt to control this estimation, the GAN components are trained together in alternating fashion, with the discriminator ideally leading the generator by a slight edge. If the discriminator gets too far ahead or too far behind, the gradient for the generator will deteriorate. One effective GAN variation for stabilizing training, called progressive GANs, begins training with low resolution inputs and gradually increases resolution until the desired quality is met. This progression of training difficulty softens the challenge of keeping the two components in balance. Another challenge GANs face, partially as a result of instability, is called mode collapse, where the generator learns to produce only one or few effective data points rather than the whole data distribution. For example, our hot dog GAN might experience mode collapse by producing the same hot dog over and over, rather than various types of hot dogs. This phenomenon occurs because, from the perspective of the generator, there is no direct motivation provided by the loss function to produce variation. Rather, at any point within the distribution can optimize the score. Two GAN variations which mitigate this issue are cycle GANs and class conditional GANs. Class conditional GANs add an additional vector to the generator's input. This vector specifies which class the generator should produce. The discriminator then makes its classifications based on that class. As a result, the class conditional generator is incentivized to produce a wider distribution of outputs in order to improve its score. Mode collapse for each individual class can still occur, but is less likely as the representation is shared between all classes. Cycle GANs reduce the chance of mode collapse further by adding in a reconstruction error term by incorporating a second GAN. The second GAN receives input from the first GAN and attempts to reproduce the input to the original GAN. The reconstruction error is added into the final loss, and by including this reconstruction error, the system is incentivized to learn to produce outputs unique not just to each class, but to each individual input. So how can we tell if a GAN's performance is improving? Unlike regression or classification models, we can't use forms of accuracy scores to directly evaluate our performance. As of April 2023, it seems most researchers rely on a collection of evaluation scores rather than any single metric in particular. That being said, there are two notable metrics I'll mention. The first is the inception score. To get an inception score, a GAN's outputs are provided to a high-performance image classification model named Inception v3. The performance, both in prediction confidence and diversity, of Inception v3 on the GAN's generated images determines the inception score. Essentially, the idea is to use a common pre-trained model as a discriminator to get a standard baseline across experiments. The inception score was popular in the years following GAN's developments, but fell out of popularity mainly because it lacked domain specificity. In other words, the training dataset for Inception v3 is not equivalent to the dataset the GAN has been trained on. So the inception score is not a comparison of the GAN's generated output to the dataset it has received as input. To address this issue, the FID score, or Frechet inception distance, was introduced. The FID score utilizes the inception V3 model, but not for its classification outputs. Rather, the activations of the final pooling layer in the inception V3 are obtained for both the input and generated images. These activations are summarized as Gaussian distributions and then evaluated using the Frechet distance. This process improved upon the inception score by providing a more relevant and specific metric to the data distribution the GAN was trained upon. Again, I want to make it clear that GANs aren't just for images. They can be configured to receive and generate whatever dimensional data we want, as long as we can keep the training stable. There are many more interesting variations on GANs that I didn't mention in this video, including some that utilize self-attention mechanisms, which have been essential in recent progress in AI, especially in large language models, which, as of right now, I think will be the topic of this channel's next series. But that's it for this series on unsupervised learning. If you got something out of it, please leave a like and consider subscribing.